This is Statistics 243 for Wednesday, October 8th at UC Berkeley. Okay, let's go ahead and get started. So the idea for today is we're going to keep exploring the mysteries of how numbers are stored on a computer and what the implications of that are for the computations we can and cannot do safely. Daniel's very excited about these mysteries, so I'm glad we have at least one enthusiastic participant. Okay, so one thing I want to point out, we're going to come back to this object in R into different pieces of it as we sort of work through some of these questions. There's another one of these internal objects in R that starts with a dot, like we saw with the dot internal of inspect, called dot machine, and it basically gives a lot of information about it gives a lot of information about what are the sort of quantities that are relevant for these questions of sort of the arithmetic that we can do and how numbers are stored on the machine. So we're going to come back to a few of these quantities that are in this list here, which is the dot machine list. But the first one I'll point out to relate to something we were talking about last time is that one of the elements is integer max. And so this is the largest integer that we can work with in R. And if we actually did the computation of 2 to the 31st minus 1, 2 to the 31st because we have 4 bytes, so that would be 2 to the 32nd, except half of those are in the negative part of the real line, so we have 2 to the 31st, and we have minus 1 because we have to account for 0, which is in the middle between the positives and the negatives. So this is actually 2 to the 31st minus 1 if you actually did the computation. So that actually makes sense. We've got 4 bytes, therefore we have 32 bits. And this relates exactly to how many different numbers we can represent with that. Okay, so the next thing I want to do is start working through trying to see sort of what some of the things are that we can do that might be dangerous. So suppose I was doing some sort of computation, and I ended up with one result I had was 0.3, and another result I ended up with was 0.2, and I wanted to know if the difference was equal to 0.1. So here I am, I'm in R, I'm going to type this into R. This looks like a pretty safe calculation, right? It's just one decimal place, I'm going to subtract the two of these, that is equal to 0.1. Okay, fine. But no, it's not. Okay, so anytime that you would be in a position of doing this, and if this were if you had in your code, if you had if x minus y equals 0.1, and you were expecting this to evaluate to true, your code would break in some fashion. Okay, so we can start to try and see what's going on to try and solve this little mystery, or maybe it's just that this is a terrible program and we should never use R, right? So we're going to see that's not actually what's going on. But, well, 0.3, that looks like 0.3. And the next one is, 0.2, that looks like 0.2. And what about 0.1? Well, it does indeed look like we should be able to subtract these two and get this, right? Okay, so another thing that we can do that will help us probe this further is we can set an option in R to tell it, show us more digits in terms of any decimal number that we're working with. So maybe what's going on here is that R is doing some rounding, but somehow this number that it's rounding to is not actually what it's storing and working with in reality. And in some sense that must be the case because we're getting this result here. So I'm going to change it to be 22 digits. And now I'm going to set A to be 0.3, I'm going to set B to be 0.2, and I'm going to look and see what A is. And now we start to get a sense that something is going on that maybe we're not fully understanding. So this number is indeed very, 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 very close to 0.3, but it's not exactly equal to 0.3. And if we look at B, that number is indeed very, 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 very close to 0.2, but it's not exactly equal to 0.2. And if we do A minus B, that number is indeed very, very close to 0.1, but it's not quite. So this is why when we do that subtraction, we don't get 0.1. And in fact, if we just look at 0.1, do you think that's going to be exactly 0.1? Maybe not. 0.1 itself is not 0.1. Right? So nothing is as it appears here. So this is what we get when we subtract the two. This is what we get when we just enter the 0.1. And this is why the equals equals didn't evaluate to true, because these are very close. In fact, they're essentially the same up to the 16th decimal place, which is going to be a number that comes up over and over again in the next few minutes. But they're not exactly the same. So the question is why, indeed. And the question of why starts to go basically to the same question you guys saw in 6th grade or 8th grade or high school or whenever it was that you thought about these things, of what is 1/3, and can I actually write it down precisely as 1/3 in decimal form? I can't. I can write down 0.33333, but I can keep writing, and I'm never going to get to exactly 1/3, right? And in fact, on the computer here, 1/3 is 0.333 only up to the 16th place, where again things start to fall apart and we start to lose accuracy here.
So it doesn't apply for
well, it does, because 0.2 is rational.
But the logic doesn't.
Yeah, have you caught me in an inconsistency here? Maybe. Say what you mean again?
Well, 0.2 is not going to be repeations forever, right?
It's not going to be, what? Say it again?
Repeating forever, right?
Well, yeah, that is true. That's true. I guess, well, yeah, so exactly what analogy am I trying to make? Basically that another way of looking at this is, well, wait, this is rational, right? This is 1/3. Wait, what's the definition? What's the definition of a rational number? I'm not even remembering these details, but yeah.
No, that's
It has more to do with what base we're working in. You could represent 1/3 in base 3 precisely. You can't represent it in base 10 precisely. And we're going to see that's part of what's behind what's going on here. Okay. Let's see. So other questions or comments at this point? Okay, so we've already seen sort of empirically that if we counted off how many numbers we have accuracy up to, we basically have 16 decimal places that are accurate, and then things start to go to hell. Okay. So that's sort of an empirical discovery, but we can actually figure out why that's the case. So let's see. So one term that I want to acquaint you guys with is something called machine epsilon, and there are a couple different definitions of machine epsilon, one of which is that it's the smallest floating point value, smallest real number, such that on a computer, 1 plus x does not equal 1. So how small can we make x before when we add it to 1, what we get back is not any different than 1. And so if we do this, if we go back to R and do this, here's what we see. We see if we add 1 times 10 to the minus 16 to 1, it just says, oh, that's just 1. So that starts to get at this question of sort of how accurate can we be on the computer. Well, if I take a number that's this small and try and add it to 1, I'm not going to actually get an accurate answer that's any different than the number I started with. But if I do this with 1 times 10 to the minus 15, I do indeed get something different. This 1 is actually in the 15th position. This inaccuracy is the same inaccuracy basically as we've already seen in the positions past the 16th position. We can actually do this with 2 to the times 10 to the minus 16, and we actually get something that's a bit different than 1. So it turns out machine epsilon is essentially 2 times 10 to the minus 16. And if we look at our special .machine object in R, double.eps is what R calls machine epsilon. And so we'll see that it is basically 2 times 10 to the minus 16. And we should indeed be able to add that to 1 and get something back that is not 1. But if we try anything that's smaller than that, we're just going to get back 1, and we're not going to have incremented 1 at all.
Is that valid, or can we modify that?
No, that is a fundamental property of how we're working, how C is working with numbers behind the scenes in R. Yeah. Okay, so to try and explain all of this turmoil that I've introduced into your lives, we have to basically go back to the basics of thinking about how does the computer represent decimal numbers? How does it represent real values? And so basically what's happening is, if we think about the early pioneers of who were trying to program computers, they had to basically figure out a very fundamental thing, which is they had to say, okay, I have disk space and I have memory, and that is in very limited supply, certainly so back in the days of when people were first working with computers in the 1950s and 60s. And so I'm going to allocate a certain number of bits, or equivalently a certain number of bytes, to represent a number. And the more bits or bytes that I allocate to represent the number, basically that's going to allow me to be more accurate in my representation of numbers, but it's going to mean each number is going to take up more space on disk, or each number is going to take up more space in memory. So there's a big compromise going on in terms of playing between those two trade-offs of how many numbers can I work with in memory or on a machine versus how accurate is the representation of any one of those numbers. So basically, the way that numbers are stored on a computer is basically in scientific notation. It looks something like this. We have some digits basically after the decimal place. We raise that by we take some base and raise that to some power. And so you could think of this as just being base 10 if the b were 10. Okay. What we're going to be doing is we're going to be thinking about base 2 because we're working on a computer, and we're going to be thinking about bits. But the nice thing I want to point out about representing numbers like this is there's a lot of power that comes from representing them where we can basically change what exponent we're raising things to. Because of the following example. Suppose we think about, suppose I was going to work in base 10 and I only had 3 digits, decimal places that I could work with. Well, then I could do something like I could multiply these two numbers together, and what am I going to get? I'm going to get 0.0144. But if I'm working with a fixed number of decimal places after the decimal point, I don't have this 4. All I have is the 0, the 1, and the 4. And so I've multiplied two numbers that I could represent exactly in 3 decimal places. But as soon as I do the multiplication, I've lost accuracy because I'm going to lose that second 4. But the nice thing is if I'm working in scientific notation, so that's what this is saying here. If I'm working in scientific notation, then basically this 0 here can basically get pushed over into the exponent part. And I can keep the 1 and the 4 and the 4 in my three decimal places of accuracy. So basically having this floating point allows me to retain accuracy even when I go from working with numbers that are fairly large to working with numbers that are fairly small. So that's why when you've heard me talk about floats a little bit or about doubles, the float comes from floating point, and we're thinking about storing these numbers in this scientific representation where we have this floating decimal point. Okay, so actually how numbers are stored on a computer is basically it looks like this. So the base is 2, and that basically has to do with the fact that the computer can most easily work in base 2 because fundamentally it's working with bits, so zeros and ones. So back in the day, originally people often worked with floating point values that were called floats that were 4 bytes for a real value. Nowadays, people, for the most part, computers mostly work with 8 bytes per real value, and so going from 4, which was a float, to 8 is double that, and so these things are called doubles for that reason. So it's basically a historical artifact. So when you hear me here talk about doubles, I mean real numbers that are represented in 8 bytes on the computer. Okay, so now if we start thinking about, suppose we've decided we're going to represent numbers as 8 bytes, and that's a compromise between representing numbers as accurately as we possibly can versus not taking up the entire memory of the computer with representing a single number, right? I mean, we could use billions of bits to represent a single number, but we wouldn't be able to do very much interesting on the computer if we did. So, okay, suppose I've got 8 bytes, so that's 64 bits. So I have 64 zeros and ones. And now I basically have a choice that if I'm going to represent things in this kind of manner, I can think about how many bits am I going to allocate to this part of the number, and how many bits am I going to allocate basically to the power that I'm raising 2 to. So, and I'm also going to need a bit that I'm going to allocate to whether the number is positive or negative. Okay? So basically this S is called the sign bit, So that S is going to be, I don't know whether it's actually when it's stored on a computer, the first one, but we can think of it as the first one. So here's S, that tells us whether it's positive or negative. And now I have 63 remaining bits that I can use. And I can allocate them here, or I can allocate them up here. And I've sort of represented these in a little bit different way. I've actually sort of written out the 52 bits here, where these Ds would be 0 or 1. Each one of these Ds would be 0 or 1. And here I'm just writing it out as a number because it's not as important for us to think about explicitly about the bits when I raise it to a power. But what people who were developing the system had to decide was how many bits am I going to put here and how many am I going to put here. So if I think about how many I put up here, as I use more and more bits up here, what does that allow me to do? And assume that I'm working with this situation where I always have this representation. I have 1 point something. Okay, so I'm always taking a number that's around 1 and raising it to some, multiplying it by 2 raised to some power. So what's good about making E bigger and bigger or smaller and smaller? Kelly?
So if you make E bigger, you can have a greater range of numerical values, but then you might, the more bits you allocate to E, the fewer you get in D, so you have less precision in those values. And
Right,
so you
so
have to reach some trade-off of how much, what's your numerical range and how much precision do you want to be able to have.
Yep. So that's essentially precisely what these folks who are doing this were trying to think through is. Let's suppose that let's ignore the minus here for the moment. Let's just suppose this whole number up here. Maybe if it's 10, then I can represent a number that's as big as 2 to the 10th. That's not very big. What is that? 1024 or something like that. If this is 100,000, I can represent a number that's as big as 2 to the 100,000. If that's a million, I can represent a number that's as big as 2 to the million. But the biggest that this is, the biggest number I can represent is 2 to that number. So I want to be able to use enough bits to be able to represent E as a fairly large number, such that 2 to the E is also a fairly large number. So for example, I would definitely want to be able to represent numbers that are like billions or trillions, because we work with numbers that are like billions or trillions all the time, right? But at some point, I'm not going to be able to represent numbers that get to be too large if I'm only using 8 bytes. But as Kelly was saying, the more and more values that I allocate up here, the fewer and fewer that I have here. And let's suppose that I allocate essentially all of them up here, and I only leave 1 bit here. Okay. So what's going to happen then? Well, I can represent numbers that are really, really big, and I can represent numbers that are really, really small, because I can do 2 to the minus. The minus 1023 is allowing me to do 2 raised to a negative power, so I can represent numbers that are really, really small. But the result is, if you think about sort of going back to the 0.012 and the 0.0144, it was nice to have the 3 digits to be able to do 144 and be able to represent basically 3 digits of values there. And the fewer of these that I have, the less accuracy I have. Okay, so the compromise that was decided is basically what you can see here, which is that we're going to use 52 bits to represent the decimal part of the number, and we're going to use the remaining 11. So 2 to the 11th is basically the biggest number that we're going to be able to get for E, because this E is also represented in terms of bits. So it's basically the last 11 bits that are being used there. So the biggest number, so E is going to represent numbers between 1 and 2 to the 11th, which is 2048. So the result is we're going to be able to represent numbers that are raised between 2 and actually I'm losing a number in here somewhere. E can be as big as 2048, so minus 1023, so that's 2 to the 1025. It turns out the biggest we can get is 2 to the 1024. I'm not quite sure where I'm losing that single number, but and the smallest we can get is 2 to the 1 minus 1023, which is 2 to the minus 1022. So I'm going to sort of put approximately equals here and just fix that by sleight of hand. Oh, yeah, so I have that here. Okay. Let's see. The other thing I want to comment on here is, well, let's see, do I want to say it here yet or not? Oh, yeah, so I want to comment on the fact that we've got a 1 here. So basically, the 1 forces us to have unique representations. So basically, if you didn't have the 1 here, what could happen? If this were, let's see. Let's say this were a 0. Well, if this were a 0, I could also set a number of these to zeros. And if I set a number of those to zeros, then basically I'm sort of having this part play the role of this, because this is the part of the number that's supposed to represent how big in magnitude things are. So basically having the 1 here basically normalizes things. So this is always saying basically what's the magnitude of the number, and this is also always sort of representing sort of the accuracy part with which we're representing the number. And so that leading 1 is something called the hidden bit. Okay, so let's go back to our, actually let me pause and see if there are questions or comments at this point. Yeah, go on.
This might be kind of off topic, but how do they do like complex numbers? Is it a different
That's a good question. I don't actually know offhand. I suspect basically there's something like this where there's some number of bytes allocated to the real part, some number of bytes allocated to the complex part, and it may very well be that there's basically 8 bytes allocated to each. But I'm not exactly sure. Other questions? Yeah, Daniel.
Imaginary numbers are not a standard data type in C, are they? For example, just have C.
I don't know actually. I don't do much with complex numbers, so I don't have any.
Two different doubles.
Oh, you have to explicitly represent them as 2 different doubles. Okay, so in that case, that sort of answers your question if we were in C, that you explicitly have to be working with 2 separate pieces. I think R has a complex type, and so it probably has some C structure, maybe where it's representing the two pieces as part of that structure, but I'm not totally sure. Other questions or comments? Okay, so let's go back to this question of what numbers we can represent exactly. We already saw that with 0.1, as long as we set options of digits to be sufficiently many digits so that we could see it, we can see that it's not represented exactly. But what if we look at 0.5? Oh, that's kind of nice. So we actually got 0.5. Right? And what if we look at 0.25? That's 0.25. Well, what if we do 0.5 minus 0.25? That's 0.25. Hey, that's pretty cool. So we actually are getting exact numbers there, and if I could do 0.5 minus 0.25 equals 0.25, and that is indeed true, right? So in some cases this works, and in some other cases it doesn't. Anybody see what's magical about 0.5 and 0.25? Kelly?
0.5 is 1 over 2 to 1. You know, it has to do with the fact that 2 is for our.
Right. It can be represented exactly in base 2, right? So 0.5 is just 2 to the minus 1. 0.25 is just 2 to the minus 2, right? So it means that we can explicitly represent 0.5 as zeros and ones in this representation, where we basically just need a single 1 and then all the rest zeros, and we can raise it to the right power here. So 0.5 and 0.25 basically they're numbers that can be represented exactly in base 2. 0.26 is not. So once we add a little bit on here, we're back to the situation we have problems. You guys could guess what's going to happen here. 1/32 we can represent exactly in base 2, et cetera, et cetera. Okay. So let me see where we are here. Okay, so I was talking about, there's this trade-off between how accurately can we represent a number and how big a number we can represent and how small a number we can represent. So basically, since we have that leading bit, which is 1 point, and then we have basically numbers that are right around 1. We've got 1 point something or something 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 raised to the times 2 raised to some number. Basically, the biggest numbers we can represent are basically 2 to whatever the maximum is here, and 2 to whatever the minimum is there. So basically, these numbers that I've written out here. Okay. And if we look at machine double max exp, did I write that here? Yeah. So if we look at this, what we would see is this is basically the largest number we can represent in R, or for that matter in C. It's the largest number we can represent as a double precision floating point. And this is in base 10. But if we tried to raise 2 to the 1024, what we would see is it's basically the same number. Okay. And if we took 2 and raised it to the minus 1022, we would see that it would give us basically this number, which is 2 times 10 to the minus 308. So for most of us, this is a very big number, and we're perfectly happy to not need to use numbers that are any bigger than that, or smaller than this, except in a few circumstances. If I were an astronomer, I might care, right? Because this number might be not all that small in some units of traveling across the solar system. But actually, this is actually very relevant for us too, because what we'll see is when we start computing log likelihoods, so when we start computing likelihoods, think about what a likelihood is. A likelihood is a product of very many values. Often they're explicit probabilities or they're individual likelihoods, they're density values. Oftentimes those numbers will be something like 0.01 or 0.001 or something like that. If we take a number of those and multiply them together as a product, it doesn't actually take us very long to get to a number that's smaller than this. Okay? So this is actually a very real consideration, not just for astronomers, it's also a very real consideration if we're working with statistical models. Okay, so I'm going to show you that we can't indeed represent a number that's any bigger than this. So I just said that this is the biggest number we can represent. And I want to see what it is in terms of log base 10, but let me just try and calculate it first. So actually, this number is returned back to us as infinity. So we've actually already overflowed here. So this is basically just a little bit bigger than the biggest number that we can represent, it turns out. Where it's right, we could sort of try and delve into the exact details of why we can't exactly represent this, but it's a little bit in the weeds in terms of what we're trying to do here. But what if we did 1 power less than that? Well, we can do that. So 2 to the 1023rd is something times 10 to the 307. So that's a little bit, that's not quite overflowing. But if we go a little bit bigger than that, we are overflowing. We're getting to be a number that's too big to represent on the machine. So I said, okay, well, another way of thinking about this is we could have been smarter about this than actually trying to explicitly calculate this on a computer. What we could have done was, if I go back to, I guess I learned this in high school. I'm not sure when you guys, maybe it was even earlier than that. When did we learn about different bases? I'm not even sure when that was. When did we learn about, anybody who was in the American educational system, when did we learn about bases? Anybody remember?
Middle school, junior high.
Middle school, okay, junior high, okay. That's longer ago for me than for you guys, so that's my excuse for not remembering when I learned it. Well, at that point, we probably all learned that you could do tricks like this. If I want to take the log base 10 of this number, I can change things around to make it into a different base, and I can do these sort of manipulations. And what we'll see is that on the log 10 scale, 2 to the 1024 is equal to 308. So that's why when we were in R, so basically, the biggest number we can represent is right around 1 times 10 to the 308, and on the flip side, the negative side, minus 1022, it basically amounts to being the smallest number we can represent is 1 times 10 to the minus 308. So these are the exact analogs of raising 2 to the power 1024 and raising 2 to the power minus 1022, except working in base 10. And that's what we saw, that's basically what we saw here with machine double X max and double X min. Okay, questions at this point? All right, let me remind myself of where I am here. Okay, so that was overflow and underflow. Anytime you start to work with numbers or multiply together numbers that are big numbers or small numbers, you run into this problem that you might get a result that's too big to be stored as a single value or too small to be stored as a single value. Okay, so the next puzzle that I want to look at is the following. So recall back to what we were talking about at the beginning of class. We said integers are stored as 4 bytes, and the biggest integer we can store is 2 to the 31st minus 1. Okay. So that tells me that if I try and raise the number 2, where am I here, to the power 45, that's going to be bigger than 2 to the 31st, right? So 2 is an integer, we're raising it to a power, that should produce an integer. So this should overflow, right? Okay, that should overflow. So x should be infinity. Huh, that's interesting. So x is not infinity. It didn't overflow. And yet we know that if we're storing things as integers, we shouldn't be able to get a number that's bigger than 2 to the 31st, which is a number much, much less than 2 to the 45th if we're now thinking about it in terms of base 10. Anybody know what's going on here? So if I frame it this way, this must be not this number x must not be stored as an integer, right? Because an integer would overflow. But what's the biggest number we can represent as a real value, as a floating point value? Well, it's around 1 times 10 to the 308. That's bigger than this, right? This is 10 to the, I don't know what, 15 or 16 or something, right? So if we, and this goes back to thinking about classes and types in R, if we say what's the class of x, it says it's a numeric. If I say what if I had a y that was as.integer of 5, and I say what's the class of y, it says oh that's an integer. So x, which I had gotten by raising 2 to the 45th, is being treated as a numeric, which is a double precision floating point value. So it's being stored in 8 bytes instead of in 4 bytes, which is why we can work with that big a number. So this actually answers one question that you guys might have had when we were first talking about. I guess I did some of this in the boot camp. I may have talked about it in class a little bit, which is oftentimes R, when you put in numbers in R, they're not treated as integers, even though you put them in without any decimal places, right? If I put in the number 5, I don't need to put in 5.0 to force it to be treated as a numeric value. I can just put in 5, and R automatically treats it as a numeric, i.e. a floating point value, instead of as an integer. Well, this is essentially precisely the reason why. Because if we were working with integer, if we stored it as an integer, it can only get to be, we can't store very large integers because of the 4-byte limitation. We couldn't store integers that are any bigger than this, but this is not a very big number, right? That's 2 billion. That's 2 billion, right? That's not a very big number in a lot of domains that we need to work in. So this is basically why R stores integers, usually stores numbers as real values instead of storing them as integers. If I tried to do the following, so I've got my x, it's 2 to the 45th, and now I try and force it to be an integer, you can sort of guess what might happen. What are the possible things that could happen if I did that? Could give me an error, could say, no, that's a problem. Or it could say that, no, that's infinity if I try and store it as an integer. So we'll see what happens. Okay, so it turns it into an NA and gives us a warning message. Okay, so I guess that's a third thing that could have happened, which is what did happen. Okay, so we.
Why does that instead of giving it infinity? I thought NA was kind of analogous to a null value.
Yeah, it's basically analogous to a missing value. I suspect the reason it's doing that is because it may have something to do with if you were storing it as a real value, R could interpret it as something less than infinity. So it might be a little bit funny if R took a number that was less than infinity, you tried to do the conversion, and then it made it into infinity. Maybe I'm not giving a very coherent answer, but
Like it would just. I think I see what you're saying, that it stops you right in your tracks as opposed to propagating some infinite value and maybe giving you a whole slew of errors later on.
Yeah, I think that's sort of vaguely what I'm trying to say. Okay, so again with this idea of how big we can work with 1 times 10 to the 308. If we tried to work with 1 times 10 to the 309, it says nope, that's infinity in R's representation of how big a number we can work with. Okay, so that was basically we were sort of talking about this big compromise that had to be made in numerics between how big a number can we represent, that's the 11 bits that are being used for the power, and how accurately can we represent a number. So we've talked through some of this question of how big a number can we represent. and the flip side is, which we haven't really talked through explicitly, but the flip side is how small a number can we represent. And now I'm going to turn to talking about how precisely we can represent a number, and that's going to get to this thing about the 16 digits that we were seeing. Yeah, Chris?
Just if you do type of infinity, it's double. So that's why.
Oh, that's interesting. Okay. So maybe there is no way to store infinity as an integer or something like that. Yeah. Okay. All right, so let's turn to precision and try and actually, let me say one more word about integers, which is, you might think that this is sort of a limitation. You might be sort of like, oh, integers, we already saw that there were some problems because we're trying to store numbers and we can't. They're not able to be represented exactly in base 2, and so the downside to storing these numbers in this representation is I have this inaccuracy in storing the numbers. So really, I'd really prefer to store them as integers and not have inaccuracy. But if you think about it, and I may actually assign this as a problem set problem, if you were to try and write out integers in base 2, what you'll see is you can write out the numbers 1, 2, 3, 4, 5, up to very, very large numbers exactly in base 2. Okay? And in fact, you can write out numbers as big as 2 to the 53rd exactly in base 2. And so we basically are not losing anything by representing integers as these double precision floating points because they can be represented exactly. So I can do things like type in any fairly large integer values, and I'm going to get back exactly this, and this is exactly the right integer. There's no inaccuracy in doing these calculations, even though these are both represented as floating points, and the result is represented as a floating point. Okay, so that's basically why R chose to do this business with turning integers into doubles, because there's sort of no cost to it and there's a big benefit to having done so. The only cost to it is that we are storing numbers with twice as many bits or bytes as we would if we were working with doubles, but that's basically the cost. Okay, so what about precision? So now we're going to sort of try and talk through that. So here's a number. I'm going to do a lot of this sort of game of writing out numbers where I put the digits in order, either 1, 2, 3, 4, and then 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. And the reason I'm doing that is it makes it easier for us to see where the inaccuracy is occurring in the number, because they're in this sort of repeating sequence. So here's a number that is, I'm hoping would be precisely this. And if I look at it, I see 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. And this is basically accurate into the 16th place, because this 9 basically rounds this up to a 4. So this is the accuracy I have here, but then after that, this is not accurate. This should be all zeros. Okay, so we saw that we have 16 decimal places of accuracy in that number. Actually, let me do another experiment here. Let me add on another 1, 2, 3, 4 at the end and see what happens. So now I have 5 sets of 1, 2, 3, 4 in here. And I can see basically the same thing. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and no more accuracy. But now let's see what happens if we start to work with numbers that are not of a magnitude around 1. Like this number is a order of magnitude that's about 1, or 0.1. But let's work with a number that's an order of magnitude of about 1,000. So now if we look at it, 4, 4, 4, 4, that's fine. Actually, even the 17th digit here is okay, but this should be a 2 and it's not. Okay, so in some sense we got a little bit lucky here that this one is accurate. So what does it look like? In this number we don't have 16 decimal places of accuracy, but we still have 16 digits of accuracy. Okay, and that's basically this idea of floating points that we've been talking about. That these bits are the ones that are responsible for the accuracy of the number. These bits are responsible for how large or small a number we can have. And the fact that we have 16 digits of accuracy, regardless of whether they're before or after, is because the floating point is able to float back and forth. And the number of digits of accuracy we have is basically based directly on having the 52 bits in that part of the representation. Okay, so you can sort of start to think about what will happen if we start playing this sort of game, and you might say, well, there are 4, 4, 4. I might expect to only have accuracy up to here, because that would be where 16 digits would be in that number. And indeed, that is the case. You can see where all hell breaks loose there. And this starts to, we can do it here. And now we actually see that we have no accuracy at any position in any of the decimal places, because we've used up all of our accuracy in representing the 16 digits that are to the left of the decimal place. And things get even worse. Here's a number where I'm trying to represent, where is it? I'm trying to represent 20, a value that's basically 10 to the 20th. And that's a number, I can represent numbers that are that order of magnitude, because we've already said I can represent numbers that are as big as 10 to the 308th, right? But I can't represent those numbers exactly. I can only represent those numbers basically up to this amount of accuracy. So again, I have 16 digits of accuracy, and this is not accurate in terms of the number that I'm trying to represent. So it's not that I can't represent a number that's this big. It's just I'm representing an approximation to a number that is that big. Okay, so any questions at this point? Yeah, Mike.
The number is after 16. Where's the R getting those numbers?
So basically, and I think we'll sort of see this maybe in a couple places. This number here is not, and I wanted to make this point before. These digits are not random and they're not arbitrary. What they are is, this is the number that can be, this is the number that is closest to the number that we want, such that it can be represented precisely in this representation. And so if we started to use numbers, if we started to add 1 to this number or 2 to this number, what we would see is that when I change this to a 5, I get the same number back, because this is still the closest approximation to this, just as it was the closest approximation to this. So I would have to add on some amount of magnitude more to get up to whatever the next value that could be represented exactly in our representation. Okay, that was a good question. Other questions? Okay, so this is going to affect what kinds of calculations we can do. So suppose I wanted to do this calculation. I want to subtract this number. So here are 8. Here's another 8. So this is 16 digits. And this is also 16 digits, but it differs by 1. So I'm going to try and do that subtraction. So that's okay. But what if I try and do this subtraction? So mathematically, obviously, this is, well, maybe not obviously because there's so many digits here, but trust me, I wrote this out such that this would be exactly exactly a difference of 1 between these two numbers. But we've already seen up here that these last 4 digits couldn't be represented accurately. And so these 4 digits here are not being represented accurately, nor are these 4 digits being represented accurately. So I'm basically trying to do a subtraction in a part of the number that I'm not representing accurately. So, and we can sort of the answer to what I went through with Mike's question should basically reveal why we get a 0, which is these numbers are basically represented in the same 64-bit representation. So I subtract them and I get 0 because there's no difference between them in our representation, even though there's a mathematical difference between them. So you can start to see why we're spending a couple of days on this. If you start to do calculations where you're trying to do this sort of thing on the computer and expecting to get meaningful answers, your code is going to go wrong pretty quickly. On the other hand, I can sort of do this, right? So what's going on here? This is the 16th digit. This is the 16th digit, so I should be able to subtract that and get a 1, and the exact answer should be 10,000. But because neither of these guys are represented precisely, there's basically this approximation involved in representing this last part of the number. The answer I get back is near 10,000. It's near the right answer, but it's not exactly the right answer. In contrast, if I were trying to do a subtraction like this, so this is the same subtraction, except, is that right? except I've just knocked off all of these digits here, which are in common between the two numbers. I can do that subtraction and get the exact answer. So this is, I guess I'm actually jumping ahead of myself a little bit. This is an example of something called catastrophic cancellation, which is all of the numbers here that are the same, which are being represented exactly, basically cancel with each other when I do the subtraction. And all that's left is one number that can be represented accurately and a bunch of parts, a bunch of digits that can't be represented accurately. And so even though I can represent 10,000 exactly on the computer, when I calculate it via doing this calculation, I don't get the right answer back. Let's see, and we can see similar sorts of things happening. Here I'm trying to do a subtraction where the right answer is 1 times 10 to the minus 16. I can represent 1 times 10 to the minus 16 on a computer. The answer I get back when I do as a calculation is basically 1 times 10 to the minus 16, but I only have 1 digit of accuracy. All of the rest of this is basically garbage. Even though I can do 1e to the minus 16, I can represent that fairly accurately up to 16 decimal places, or actually up to 34 or 36 decimal places, or whatever it is, up to 16 digits in this case. But that's because I just typed this number in and was just trying to represent the number. When it comes from a calculation where the calculation starts with a number and where this cancellation happens, where I'm basically canceling all of my accurate digits, then the answer is represented much less accurately. Okay, so we're going to come back to that in more detail next time and sort of see how this relates to the fact that we have 52 bits allocated to the accuracy part of the number. But let me quit here with a couple minutes left to ask about the project deadlines. So the last day of classes is like Friday, December 5th. That's the week after Thanksgiving. And then the next week is reading week, so that's Friday, like December 12th. And the next week is exam week up till Friday the 19th, and then we have the break. So I don't really care personally when the projects are due within exam week or reading week, because I'm just going to be here and I'll grade them when I get them. So I wanted to get some feedback from you guys of whether you had a preference. Obviously the trade-off is you either have to stay longer potentially and it might be cut into your time of studying for exams, versus you have less time to do it and you may feel more pressure during the reading week. So how many people would prefer to have the project due at the end of the reading week, like around December 12th or so? Oh yeah, right. I should tell you what the options are before I ask you to vote. Right? So I think the options are the end of reading week, December 12th or so, the beginning of exam week, say December 15th or so, if I'm getting the dates right, or the end of exam week. Okay. So December 12th or so? Okay. December, that Monday or Tuesday, December 15th or 16th or so? Okay, and what about the end of exam week, December 19th or so? Okay, so I think the 12th wins. Before I let just majority rule win the day, for are there any people who, if it were due December 12th, well, let's see, how do I want to phrase this? Well, there is that, right? If I just asked you to vote based on if it really, really matters to you versus just a slight preference, how many of you really, really want it to be due December 12th? Okay, a few of you. And how many of you really, really want it to be due December 19th? Okay, so it's okay. All right, so let me think about it a little bit, and I will get back to you. I'm probably, last year I assigned this, and I'm probably going to do the same thing. I don't. Probably early November. Why are you asking?
I just want to know if it makes sense to kind of drop the class instead of trying to move it down.
I will. No, I'll. Before I assign the groups, I'm going to do a check-in and see who's officially in the class, who might not stay in the class. So I'll try and take care of that.
Because I'd like to, but if the material is stuff that I just
Yeah, and I actually wouldn't worry about that. You know, if I don't decide whether to drop the class based on what you feel like, based on some thought that you might particularly because part of what I'm doing by randomizing the groups is trying to make sure there's a mix of people with different experiences, and so that should.
Yep, on the syllabus or something like that, you mentioned that you might have